Now, let us consider about one more quantity which is very much useful and essential in evaluating the effect of charge in the space is the electrical field. See, one thing from very beginning I am telling that when there is a charge in the space, it has the nature to apply force on another charge or on another object. In fact, on another uncharged object experiences the force due to any particular charge is due to the reason that the object gets charged by induction, and in that situation when both the objects are having charge, there exists a force in them. Now, what is the strength, what is the ability of charge to apply force on other objects? In what way we can justify this? Like, let us say a charge Q is there kept, and another charge is kept at a certain point in the space. Then what extent of force it will experience? Of course, we can find it with the help of Coulomb's law. But the nature of Q, the nature of the charge due to which we are experiencing the force, in what way we can declare this nature? The ability of given charge in applying force on other charges is justified in what way? What is the influence of the charge around it in applying force? For all these considerations, we need to define another quantity, and that is called the electric field. In fact, by field you can clearly assume in the mind that it is defining the space around the charge in which its effect is applicable. The space around the charge, up to what space, up to different points in the space, in what way the charge has the nature to apply force. This is justified by assumption, or by itself you can assume by keeping the Coulomb's law in the mind, that the force is depending on the value of charge, and also depends on the distance of given charge from the charge creating the environment. So of course it is depending on distance and the position vectors also, because this is applying a force, and the force has a direction, and that direction is along the line joining the test charge and the charge in which this influence is tested. So it is totally depending on the position vectors. So at each and every point in the space around a charge, the influence is different, because each and every point is having a different position vector. Suppose the test charge is here, you are keeping the test point here, you are finding the influence at this point, so it will be in this direction or in this direction along this line. Your point is suppose here, then it will be in this direction or in this direction. So around the test charge, wherever the point is there in the space, the influence of force is specific to that particular point. So keeping all these things in mind, let us see how we can define the field influence or the charge influence, and we can declare this as the electric field. According to Coulomb's law, force between two charges kept at two charges Q1 and Q2 kept at a distance of r meters apart, kept at a distance of r apart, is expressed as F equal to 1 upon 4 pi epsilon 0 into Q1 Q2 upon R square. R is the position vector. Let us consider a charge Q, capital Q. Around which its influence has to be justified. Assume a test charge Q is kept at a distance R from Q, having position vector R. The force experienced by Q due to capital Q in this situation is F equal to 1 upon 4 pi epsilon 0 into Q, capital Q upon R square, having position vector R. Now In order to express the influence of capital Q at R, let us assume Q equal to 1, that is 1 coulomb. Thus F equal to 1 upon 4 pi epsilon 0 into capital Q upon R square R. Now this is the force experienced by charge Q on unit positive charge when placed at a distance R from Q having position vector R. This force is called the electric field. And is denoted by capital E. Thus, E can be written as 1 upon 4 pi epsilon 0 into capital Q upon R square R. Electric field at a point, electric field due to a charge at any point around it is the force experienced by the unit positive charge placed at that point. Of course, E can be written as F upon Q. and hence its unit is Newton per Coulomb NC minus 1. As it is observed here, that the field is independent of the value of test charge Q whatever the value of Q is taken, the force experienced is Q times the field, that is F equal to Q E. In fact, this is true even for the smaller value of charge also. As Q is small, F will also be small, and the ratio comes same. Thus, field can be written as limiting value of Q tending to 0 F upon Q. Let me repeat again that this quantity field which is having the unit as Newton per Coulomb is telling about the characteristics of the charge in applying force around it. It is a measure of the influence of a particular charge around the space where it is placed. It tells about the strength of charge in applying force around it in the space. So this is actually its physical significance in electrostatics. Now, as individual charge is applying individual force, then when a system of charges are there in the space, like one charge is kept here, one charge is kept here, one charge is kept here, system of charges are there in the space, and around that, if you want to find the field by the influence of all the charges, or what is the effect of all charges around it in applying the force. So normal vector summation concept can be considered here also, that the total field on a particular point in the space where a system of charges are kept together is the vector sum of all the fields. So let us consider a number of charges Q1, Q2, Q3, Qn are placed in the space, and one has to find the field at any point by this system of charges, then it is necessary to take vector sum of all the fields created by individual charges. If fields created by individual charges are Q1, Q2, charges are E1, E2, E3, so on up to En, then final field can be written as E equal to vector sum of all the fields. See, here again and again I am using the term vector because direction is implicitly attached with it. Without direction you cannot talk about the force. Field is also a force in a specific situation. Again I repeat that field is used to find the influence of a charge in applying force. We are standardizing the influence. When some standard quantity is there for a particular charge, then in terms of that standard quantity one can declare the force, one can quantitatively find the amount of force. So this quantitative declaration of influence quantitatively is the field, and direction is of course attached. Without direction you cannot think of the field. Suppose a point is here, you want to find the influence at this particular point. So charge is here, given charge is here, test charge is here, of course it will apply the force in this direction. So at this particular point field direction is this, towards this. So field is a vector quantity. So all the mathematical manipulations, all the mathematical assumptions, in fact the practical assumption of this particular field, this particular influence is done in terms of force, and ultimately it's a vector quantity. Now let us consider, before I go onwards, let us consider the two problems given in your book related to this field term. See, one problem is here. Let me zoom it to show you. An electron falls through a distance of 1.5 centimeter in uniform electric field of magnitude 2.0 into 10 to the power 4 Newton per Coulomb as shown in the figure. The direction of the field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case. Now here gravitational influence is not considered. Now we have, this is problem 1.8. There is electron and this is charge Q. This strength is E equal to, magnitude of E is 2.0 into 10 to the power 4 Newton per Coulomb, and this distance is 1.5 centimeter. Charge on electron is 1.6 into 10 to the power minus 19 Coulomb. So force experienced by the electron due to field F equal to Q into E, that is 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4. Mass of electron is 9.11 into 10 to the power minus 31 kilogram. So acceleration produced equal to F upon m, that is 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4 upon 9.11 into 10 to the power minus 31. Now, in order to the equation of motion gives the relation between time of fall t, distance h, and acceleration a as h equal to half at square. So t equal to 2h upon a square root. That you have so many problems you have solved in the motion problems. So let us put it all together. Time of fall equal to square root of 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4 upon 9.11 into 10 to the power minus 31. This is, just wait, let me write in a proper way. T equal to under root 2 into h is 1.5, that means 0.015 in meter, and a is reversed, so a is inversed, so let us write the denominator part first. 9.11 into 10 to the power minus 31 upon 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4, and whole is under the square root. So let us calculate it. It is 2 multiplication 0.015 into 9.11 divided by 1.6 divided by 2. So this is 0.0854, and let us calculate its square root. This is coming as 0.2922. So this is equal to 0.2922 into square root of 10 to the power minus 31 minus 4 plus 19, that is square root of, this is 35 and minus 19, it will be this is 15, this is my 10 to the power minus 16, that is the whole is 2.2922 into 10 to the power minus 8, and finally t equal to 2.9 into 10 to the power minus 9 seconds. Now, when this is considered in case of proton, I don't want to discuss this once again, but when this is considered in case of proton, you need to have only change in calculation, only the mass will change. As you will replace the mass in this, the expressions are same and the time can be calculated. Example 1.9. We have the two charges Q1, Q2 having the value plus 10 to the power minus 8 coulomb, and this is minus 10 to the power minus 8 coulomb. Point A is here at the midpoint. The distance between this is 0.05 meter. This is also 0.05 meter. Now point B is here. This is 0.05 meter. And point C is here. From Q1 it is 0.1 meter, and from Q2 it is 0.1 meter, and from Q1 also it is 0.1 meter. See, total field at A. This we are going to calculate. So first of all, field due to charge Q1 E1 equal to E1 equal to 1 upon 4 pi epsilon 0 into 10 to the power minus 8, the value of charge, upon 0.05 whole square. Along BA, here since it is repulsive force, and field due to charge Q2 E2 equal to 1 upon 4 pi epsilon 0 into 10 to the power minus 8 upon 0.05 whole square. This is along BA, that is towards Q2. This is attractive force. So as both the fields are in the same direction, they are simply added to find the magnitude of resultant, that is E equal to, directly I am writing 1 upon 4 pi epsilon 0 into 2 into 10 to the power 8 minus 8 upon 0.0025, that is 9 into 10 to the power 9 into 2 into 10 to the power minus 8 upon 0.25 into 10 to the power minus 2, let us say. So just multiplying this by 4 will give 1 in the lower part. So it is good to multiply. So 9 2's 18 and 4 72 equal to 72 into, this is 9 minus 8 1 and this 2 will be here, so it is 10 to the power 3, and finally it is 7.2 into 10 to the power 4 Newton per Coulomb. So this is the first case solved. Now for the second case, this is field at point B. Now let us recall this again. We have the figure here, point B is here. So the distance between B and Q1 is 0.05 meter and distance between B and Q2 is 0.05 plus 0.05 plus 0.05, altogether 0.15. So on this basis the calculations will be done. you know, field due to Q1 equal to 1 upon 4 pi epsilon 0 into 10 to the power minus 8 upon 0.05 as usual whole square along AB, that is away from Q1 towards B as repulsive force exists. That is, this much I am writing just to make you understand all these things clearly, that in what way the things are simulated and the things are visualized and experienced and understood to imagine the full situation, and then only you can calculate the things properly. So E1 equal to 9 into 10 to the power 9 into 10 to the power minus 8 upon 0.25 into 10 to the power minus 2. This is equal to 9 by 4, this will be multiplied, then 3.6 into 10 to the power 1 here and minus 2 becomes 3 here, and finally it is 3.6 into 10 to the power 4 Newton per Coulomb. Now as again you will calculate field due to Q2 E2 equal to 1 upon 4 pi epsilon 0 into 10 to the power minus 8 upon 0.15 whole square. This is along BA, that is towards Q2 as force being attractive. So E2 equal to 9 into 10 to the power 9 into 10 to the power minus 8 upon let us say 0.0025, that is sorry 0.0 0.0225, that is this will be 4, I think. 2.254. Yes. Then it is 4 into 10 to the power 1 into 10 to the power 3. So equal to, let us divide, 9.9 divided by 0.0225. So it is 400 into 10 to the power 1, and finally it will be, that is E2 equal to 0.4 into 10 to the power 4. So finally it is observed that being closer to Q1, point B is closer to Q1 than Q2, so influence of field of Q1 will be dominant. So and here also you are seeing that this force is more, so this is E equal to 3.6 into 10 to the power 4 minus 0.4 into 10 to the power 4, and altogether this implies that 3.56 into 10 to the power 4 Newton per Coulomb. This is at B. And now see at point C. Point C is here. Now at this point, this is positive charge, this is positive charge. So force due to Q1 is in the direction of BC. And here you see this is negative charge, this is positive charge. So force due to Q2, field due to Q2 is attractive, and it will go along CQ2. That is CQ1 and CQ2, not B. So resultant will somehow come in this direction. Now field at C. Field due to Q1 E1 equal to 1 upon 4 pi epsilon 0 into 10 to the power minus 8 upon the distance is 0.1 whole square along write like this, towards Q1 from C. No, not towards. away from Q1 away from Q1 at C, being repulsive force. So E1 is ten to the power 9 into 10 to the power 9 into 10 to the power minus 8 upon 0.01. That is 9 into 10 into 10 to the power 2, that is 9 into 10 to the power 3 Newton per Coulomb. And you know, field due to Q2 E2 is same in magnitude of E1, but direction is towards Q2 from C as the force being attractive now. It is somehow like this. The angle between these two is 120 degree. So resultant E equal to E1 square plus E2 square plus 2 E1 E2 cos 120 degree that is since both are same, E square plus E square plus 2 E into E into minus 1 upon 2. So finally it is E. So the magnitude of that is 9 into 10 to the power 4, I think 9 into 10 to the power 3. The magnitude of resultant equal to 9 into 10 to the power 3 along along the line joining Q1 Q2. Towards Q2. That's it.